The engine's operating temperature will vary considerably, from the time when it is started from cold to when it's been running at high power for long periods of time. The oil's viscosity must stay within required limits to do its job, and the range of temperatures within which it can safely do this is called its viscosity index. There are various standards employed to determine the viscosity or thickness of oils. They all provide a datum by which differing oils can be compared. Obtaining these standards requires that we measure the time taken for a fixed quantity of oil at a given temperature to flow through an orifice or jet of a given size. There are two standards that are generally employed in aviation to indicate the viscosity of oils. These are the Society of Automotive Engineers, SAE, and the Commercial Aviation grading systems. Both systems use numbers to indicate the viscosity or the grade. The lower the viscosity number, the thinner the oil. From this diagram, it can be seen that the SAE number is generally half that of the commercial aviation system. Lighter loaded engines use a low viscosity or thin oil, whereas higher powered engines with higher loading would require a high viscosity or thick oil. As previously stated, the air temperature in which the engine operates also has an influence on the viscosity of the oil selected for use in that engine. For example, a light aircraft operating within the United Kingdom during the winter may use an 80 grade oil, and in summer it would use a 100 grade, the choice of the grade being dependent on the average ambient temperature. The use of too high a viscosity oil at too low a temperature can cause engine starting problems. Oils which have two viscosity values can be used to minimize starting problems. For instance, SAE 15W50. The W indicates that the oil is suitable for use in winter in cold climates. Oils with two viscosity values are called multigrade oils. They will have the characteristics of low viscosity at low temperatures and high viscosity at high temperatures. The type of oil used in aircraft piston engines is normally mineral-based. If the oil contains no additives, it's called a straight oil. To meet certain requirements of engine operation, additives can be mixed with the oil. These additives can take the form of antioxidants, dispersants, and oiliness agents. Oils which contain additives are called compound oils. Straight and compound oils are both identified by the viscosity numbering system, but a compound oil will have additional lettering as well as the number. Thus, a bottle or can containing a straight oil with a viscosity of 100 would have only the number 100 marked on it. But a compound oil of the same viscosity may be marked AD100, EE100, or W100. The actual lettering used varies with the oil's manufacturer. The letters AD, EE, and W all denote that the oil is an ashless dispersant oil. The W on the Aeroshell W100 oil, which is produced by Shell International, should not be confused with the W used in the grading system. Generally, straight oil is only used when running in new engines, or for specific engine installations. As we said earlier, piston engines normally use mineral-based oils. However, some engine manufacturers have trialled and approved the use of semi-synthetic oils. Indications of oil pressure and temperature give the pilot a good idea of the mechanical integrity of the engine. Of course, the pilot must then interpret these indications correctly. Aircraft which use radial and inverted engines require the pilot to have knowledge of the lubrication system even before he starts the engines. Both of these types of engines can suffer from a problem called hydraulicking. In radial and inverted engines, oil may accumulate in the cylinders at the bottom of the engine, between the piston and cylinder head after shutdown. Damage to the engine could occur on startup, as the piston, on the compression stroke, traps the incompressible oil between itself and the cylinder head. Prior to starting, these engines should be rotated through a number of cycles by use of the propeller, to ensure no hydraulic lock has occurred. You must, of course, ensure that the magnetos are off before turning the engine over. After starting an aircraft piston engine, positive engine oil pressure should be indicated within a specified time. The Piper Warrior checklist stipulates 30 seconds. If oil pressure is not indicated within the specified time, the engine must be shut down immediately and the problem investigated. If the engine is started from cold, initially the oil pressure could appear to be excessively high. This indication can be considered to be normal, as long as the pressure drops to within its normal range as the engine warms up. Correct engine operating pressures and temperatures are dependent on each other. As was stated before, as long as the oil pressure drops to normal as the engine warms up, this situation can be considered acceptable. However, if the pressure rises to dangerously high values, the engine must be stopped to prevent damage. The oil pressure should be within its operating range at the correct operating temperature. High oil temperature could cause the pressure indication to be low. If the oil pressure is too low, apparently because of associated high oil temperature, then this is probably due to the viscosity of the oil dropping below the point where the oil pressure relief valve can cope with the situation. If the engine is fitted with oil cooler shutters, then they can be opened in an attempt to lower the oil temperature. Alternatively, if oil cooler shutters are not an option, then consideration should be given to either reducing engine power or lowering the nose to increase airspeed, or even making the mixture richer. Any or all of these actions can be used to cool the engine and thus cool the oil, bringing its viscosity back up to the point where the system can cope. If the oil temperature is within its correct operating range and the oil pressure is still indicating that it's too low, then it's likely that there is either excessive clearance on the bearings due to wear, a defective pressure relief valve, or, potentially even worse, leaks from the output side of the pressure pump. If the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage being caused to some components through lack of lubrication. Fluctuations in pressure could be the result of either low oil levels or system faults. Small fluctuations of the oil pressure gauge needle, either side of the desired pressure, may be indicative of a sticking pressure relief valve. This would cause the pressure to first build up beyond the optimum level, then subsequently, when the pressure reached a point high enough to overcome the stiction of the valve, it would open, dropping the pressure momentarily below the correct level. Then the cycle would start again. Large fluctuations of the oil pressure gauge needle, on the other hand, will probably be caused by insufficient oil in the system. The engine may have been leaking oil, and eventually the level will drop to a point where the pressure pump cannot sustain its output. Then the pressure will drop momentarily until the pump can get some more oil, when the pressure will rise again, if only for a moment. If the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage. If the oil pressure falls suddenly to zero, then perhaps the reasons may be a bit academic. After all, if the minimum oil pressure cannot be maintained, then the engine must be stopped to prevent damage, and there is probably not a lot you can do about the problem. Nevertheless, the probable cause is either failure of the pressure pump or a total loss of oil. Coring is a condition which can occur in engines which are capable of developing very high power outputs. During the climb to height, inexperienced operators would sometimes tend to set the oil cooler shutters in a fairly open position, to ensure that the oil temperature stayed cooler rather than hotter. Unfortunately, if the ambient temperature fell faster than anticipated during the climb, the oil temperature would fall lower and lower. The viscosity of the oil flowing through the oil cooler would rise, and eventually the oil would become so thick that in the front of the cooler the oil would stop flowing altogether. To the rear of the cooler, some oil would still flow, but being insulated from the cooling air by more and more stationary cold oil, it would get hotter and hotter. The instinctive reaction of the inexperienced operator to the indications would be to open the oil cooler shutters fully. But this would just cause the oil temperature to rise faster by thickening the insulating layer of cold oil in the front of the oil cooler. The correct actions to take would be to close the oil cooler shutters. If this is done soon enough, the heat of the oil in the core is passed outwards to oil in adjacent tubes in the matrix, lowering the viscosity of the oil sufficiently to start flow through the rest of the cooler, increasing the volume flow and thus eventually dropping the overall temperature of the oil contents. It should be appreciated that as the oil is used to lubricate the moving parts of the engine, it will come in contact with the combustion gases. The inlet and exhaust valves and piston rings do not have a 100% seal, and as a result some oil will be burnt, and the engine will therefore have an oil consumption rate. Oil consumption varies between engines. A typical light aircraft engine would use around 1 pint per hour, although some engine manufacturers consider 2 pints per hour to be acceptable. A consumption rate greater than the recommended limit may be an indication of engine wear. The oil contents should preferably be checked prior to flight. However, if the engine has a dry sump lubricating system, the oil tank contents should be checked immediately after the engine has stopped, realistically within a few minutes of shutdown. This ensures that the contents are recorded accurately before the oil migrates, under gravity, down into the engine sump. Large piston engines have oil tanks fitted with a check valve, usually situated underneath the oil tank, which is closed under spring pressure or alternatively by an electrically operated actuator on engine shutdown. The closing of the check valve prevents oil migration into the sump. The wet sump system requires the opposite treatment. A period of at least 15 to 20 minutes should have elapsed after engine shutdown before the contents are checked by using the dipstick in the engine sump. This concludes the lesson on lubrication.